presentation from LOΗC DENEUVILLE Total Energies in collaboration with Emmanuel Sauger, the team comparative study between IOGP and ISO valve fugitive emission requirements.
Okay, sorry, it's going to be French-English again, so a lot of French-speaking people this morning. Okay, so good morning, everybody. So my name is LOΗC DENEUVILLE, and I'm working for Total Energies. So I'm located in France, in Paris, in the Total headquarters, and I'm part of our new technical entity. So just to explain for some of you that may know Total Energy, previously Total before, so with the ESG transition and all the change, it has been decided that as we are an integrated company, we'll have one technical group. So now we have one technical entity which is called OneTech that covers all the technical aspects of our business. So going from more traditional business, the upstream, the downstream, but also covering all the new businesses, like we talk here about hydrogen, biomass, even wind and solar, which we are pretty big at right now. So, and as part of this group, I'm actually in the technology department, in the static equipment team. I'm actually in the same team as Christian, and I'm the valve SME for Total Energies. So working for all valve aspects, so for any type of business for Total. So they come to us. So today I'm happy to be here. Thank you for staying. And I will present to you a study we did with Emmanuel Sauger, that is here from CETIM, with a co-author, regarding some comparison we did between the IOGP specification, which is a fairly new specification that has come out a couple of years ago, and the ISO, which is, I would say, one of the first fugitive emission specification that went out and has been around for quite a while. I think maybe, I'm not sure, 15, 20 years or... And so all this work was done with CETIM, which is a lab, a reputable fugitive emission lab in France, in Nantes. Okay, so just to give you a little bit of background. So why are we doing this? So as I mentioned, reducing fugitive emission is key to Total. It's key to Total Energy to achieve carbon neutrality. So we have a commitment to go to net zero by 2050. And out of that, we have some emission from methane. And sorry, it's not the right slide. I changed it. But you have to keep in mind, so we have a lot of CO2 emission, but we also have some methane emission. So why methane emission is very important for us? Because if you look, methane has a global warming potential, which is 25 times higher than CO2 over a 100-year period. So considering, so if you have a volume of methane, and you have to compare it to 25 the same volume of CO2. So even if we have lower volume of methane emission per year, when you use this 25 multiplier, it becomes a very big, very huge amount. And on top of that, from all the emission we have now, yearly emission, 11% of the methane emissions actually come from static equipment. So meaning piping flange and valve, and there are mainly valves. So the rest, you can ask where they're coming from, the 90%. So it's mostly from flaring. As you may be aware, or even you go around refineries or upstream, you see a lot of flares that are burning gas. So this is something that is going to be really forbidden, and we are trying to close all these flares. And this is a big initiative that we have at Total Energies and other people have as well. So once we have that, we still have a number of emissions that's going to come out of the valve. And you say 11%, so it's still a fairly big amount of methane. And on top of that, the commitment that has made Total Energy to the investors, to the shareholders, is to reduce our methane emission by 80% from 2020 to 2030. So that's a big decrease. So how can we achieve that? Well, we need everything, but we really need valves that are low fugitive emission. So what happened in 2019? There was an initiative led by IOGP. Maybe some of you don't know this, this initiative. So IOGP stands for International Oil and Gas Producer Association. So we come around with several oil majors. There was 12 oil majors, so Total Energies, BP, Shell, ExxonMobil, all the large players. And what we realize is with the current standard of API, on here, API 6D and API 600, we all had additional requirements on top of these standards. So which kind of drive crazy suppliers, because if they do a valve for Total Energy one day, then they do it for another supplier, another operator the next day, then they have to keep in mind that they have to change the requirements. So the idea was to, okay, let's be together and try to come up with a common set of requirements for valve. So hopefully it makes life easier for everybody, for the operator, but also for suppliers. So we come with a common set. And as part of this work, it was decided within the group that already fugitive emission was a key topic. So we decided, so in addition to what's in API 6D, because it's really the topic here, which has no requirement for fugitive emission, we will add an extra set of requirements to ask for fugitive emission rated valve API 6D. So we met around and went, selected, went through consensus of operator, and what we decided was to use the ISO as a base, and in addition to that, based on the operator experience, we added some extra requirements. So we were all happy, so it was published in 2019, but from our end in Total Energy, we didn't really know, what was the big difference between the IOGP's extra requirement we put on the ISO, so we decided to launch a study with SETIM to kind of see the key modifications, the key difference. So what we did, we took, I guess, conventional upstream ball valve, API 6D, and we did a series of tests with both procedures just to compare the different parameters and see what we would use. The objective is really to see, okay, what would be in the future the best procedure so we can get the best fugitive emission valve for our assets. Okay, so if you go down, it's really in the heart of the topic. If you look at the two documents, the IOGP that is based in API 6D and the ISO, you have basically three main differences. You have a number of different, but so in IOGP, basically sniffing is permitted. Whereas for ISO, we go for vacuum or accumulation method. So what, as it was explained before, sniffing is a good technique, but you don't always collect, all the helium. So it could be more challenging. So this is one of the main differences, but sniffing, on the other hand, is a lot more convenient because you don't need so much special apparatus to do that. So the idea is say, okay, let's try the both methods and see if we can compare the results. So yeah, sorry, so for the ISO, what I forgot to mention, so you have the part 1 on part 2. And basically the part 1 is a prototype, and the part 2 is a production testing. So part 1 is what we compare with here. So we are only talking about the prototype testing. The other thing we compare was the measurement fluids. So for ISO, so here we were talking with helium. Why helium? Because we want to be able to do some production testing. So we are happy to do prototype. Prototype is good, but we want after, when you make 1,000 valve or 10,000 valve, to pick a couple of valves and to double check that what we have seen in the prototype testing is transferred in the production. So it confirms that you have the right quality management in place on everything. So for IOGP, so we agreed, so we'll use the helium, so 97% helium mixture, but we also were conscious that one of the things that is going against ISO is the fact that helium is considered as being a scarce resource. Right now, we don't really have any issue with supplies, but one of the things when you go out, they say, okay, why do you use helium? You know, it's a very rare resources, and we'll go run out of helium at some point. So you should not use helium to just to do this testing. So the idea is say, okay, if we go to the larger size, instead of using 100% helium, let's try to use just 10% helium with nitrogen. So in this study, we basically run the two tests to see if we could find the right correlation. On the third one, main one is in terms of thermal cycles. So the principle of IOGP was to run one test and go from the lowest design temperature to the highest design temperature. So here is a typical ISO IOGP, so 200 cycles, 205 cycles. So you start with 50 cycle and ambient. Sorry, after you go at the highest temperature, the other 50 cycles. After you go back to ambient, then you go to the lowest temperature. Sorry, I'm not. So you can see on the screen, so you go at the bottom, you have the cycles. So you go highest temperature, ambient, highest temperature, ambient temperature, lowest temperature, and back to ambient. So if you want to do the same thing for ISO, you actually have to do two tests. So instead of doing 200 cycles, 205 cycles, you would have to do twice the same. So you would have to do 400 cycles. So the idea was, okay, let's try to combine both tests and see if we get the results that are similar or meaningful. Okay, so what we did, we took a valve and developed a series of programs. So we run we run the IOGP protocol, we run the ISO protocol, we run with 97% helium. So the temperature we choose maximum temperature we choose was 150 C, and the lowest was -29 because the valve was with O-rings, which is a typical sealing configuration we have in our upstream application. And 150 is probably the maximum we see, even if typically our piping class are 200 C rated, but that's kind of, it's not really what we see mostly in our asset. And -29 is really being that's the limit for O-ring use. So we try to do a test matrix to try to test different variation with different test protocol. The idea not to be running, 10 tests of the same thing, because we had a limited amount of time and we didn't want to spend, months on months. The idea was to kind of get a flavor of the differences to see where we will go from there. So the test valve we used was a typical API 6D 3-mounted ball valve, 6-inch, class 600. And the only change we made was basically on the stem. So you can see on the right side the sketch of the stem. So you basically you see the stem come from the body side. So you have two O-rings. After you have the hole drill, and then you have another rings plus the back ring in the end. So the idea was, we basically took the parts we would use for stem injection and replace it and put a nipple with a tube, so we could be able to do the measurements. And just so we keep the things quite realistic. So after each test, we basically changed the sealing system. So we started with a new sealing system. So we didn't really have any impact of going from test 1 to test 6 or 7. And it was automated with an electric actuator. So it's just to mention, so it was not really high cycle. It was fairly low motion going from open to close. So in terms of test setup, so as I mentioned, so we went from 150, which was the maximum design temperature, to -29. So on the left side, you can see, you can see the high temperature side, so typical arrangement with blankets. So you can see the helium coming in the valve, and then you have the collection through the mass spectrometer. Also after for the not cryogenic, for the low temperature, so differently. So we cool down with liquid nitrogen. So because it was only -29, of course, we didn't put, pure liquid nitrogen. It was just basically a spray of liquid nitrogen just to keep the valve down at -29. So after each test, just to mention it, we didn't really see any degradation of the sealing arrangement. We only noticed some graphite particles stick on the stem. So just to give you an idea, we did about 6-7 tests, so it was about 1,500 cycles. So the valve was in good condition. On the picture in the middle, you can see the sealing arrangement. So you can see the O-rings, the 3 O-rings. And I think you can also see the graphite backup in the back. It's not very clear, but on the right side, the O-ring. So we didn't really see any degradation on the O-ring. So everything went quite smoothly and as expected, and it was good because we didn't really want to have any additional variable that come into the testing. Okay, so going into the test measurements. So this is going to be, I would have need you to be focused because it's a bit more complicated to do. Oops. So if you look at the bottom, at the apps, you have all the cycles. So you go from 0 to 205. And sorry, I'm going to, so I can do both. So we started on you have the temperature. So you go, the red one is the temperature. So between cycle 50 and cycle 100, the red one shows we go to 150. After, from 100 to 150, we'll go back to ambient, and then the lowest temperature and back to ambient. And what you are interested to look at is actually the fugitive emission measurement, which is the green part. And you actually have the line, which represents the leak rate performance. So you have the A leak rate performance, the AH, the BH, and the CH. So the BH is the one we are most interested in, is a light blue one. The H is a purple one, and the CH is amber one. So what you can see from this graph, so first we started to try to do the sniffing method, but it was found to be really difficult to implement. So why? Because we could only see very large variation of the leakage, and it took us a very long time. Even if you have this tube, and we are sniffing at the tube, it took us a very long time just to get the helium coming through the tube. So eventually, because of some time constraints and testing constraints, we actually gave up that method and went to the vacuum method, which is a lot more easy and quick to have good readings. So what we could see from this test, by going, doing one test, one high temperature design on one low temperature. So if you go to the high temperature, you start with a valve which is really good, below AH rating. Then you go to high temperature, you go above the BH class. Then you go back to ambient, it decreases. So BH here, then you go back to ambient. You go at below, slightly below, because you still have. So you reach the BH at 250 because of the permeability of the elastomer, which is kind of expected. Then you go back to ambient. You still have some helium in the polymer, so it's getting stabilized. And then when you go back to -29, when you see a sharp increase, which is also kind of expected because the TG of the elastomer we use, which was RGD elastomer, is -9. So if you go to -29, your elastomer is getting stiff. So then you start having leakage. So based on this test, we're pretty happy. So we showed, the IOGP protocol was quite meaningful. Not only not for the sniffing, but for the fact that the only one thermal cycle will show some representation. After, if we compare the same test, with an ISO test, but it's the high temperature, so we actually got the very same results. So it was actually pretty good. And so the IOGP is on the left side, and the ISO is on the right side. The good thing about the ISO is you can get some reproducibility whereas for IOGP you only have one shot, so you go just one time at high temperature. So you have less room for error. So. Similarly, we did the same test at minus 29. So interestingly enough, if you remember the IOGP curve, which is on the left side, when we are going at minus 29, because of the, you could see the sharp increase, because we go below the TG of the elastomer. But the issue with the IOGP is we didn't reach the plateau. So you could see it's going up, but we don't reach the plateau. So on the left side, you can see the ISO when we went twice at the low temperature, which is on the green part, you can see we reach the plateau and we actually reach the CH class region. So for that, the ISO was found to be probably more meaningful for the low temperature. So in terms of mixture, as I explained to you, we're trying to use just 10% helium instead of 100% helium. Actually, we found that 10% helium worked quite well. You can see on the curve, so we did 2 tests with ISO, so with 2 high temperature at 150. And you can see the green curve, so you have the same trend. It's just for 10% helium, you have a lower fugitive emission rate, which makes sense because you have less helium. And actually what we found in IOGP, the factor that is given is 10, and what we actually found in the results was between 6 to 9. So it was not perfect, but was expected, but the factor 10 seems to make sense if you want to see a trend. So same for 10% helium, but at low temperature. The issue we saw here, it's basically we didn't really see any increase of fugitive emission at the low temperature with 10% helium. So what we interpreted that was there was not enough helium to show the lack of tightness, even if the O-ring was getting rigid. So for that was quite interesting. So just to conclude, so basically we did this test just to compare the two methods. So we use a typical valve that would use mostly in an upstream application. So in terms of influence of measurements, we found the sniffing method, which is quite interesting, quite convenient to put in place. But on this test campaign, we didn't find it to be really, how to put it, successful. So we need to look at that for more. In terms of the fluid, so the 10% helium instead of pure helium seems to make kind of sense. However, with the 10% helium, we didn't keep the loss of tightness, which is kind of expected with O-ring at minus 29. So it can show some, I would say, some misinterpretation. One of the things which was quite interesting as well is in terms, helium is quite an expensive gas. So when we started that, the idea also was to say, okay, if we use 10% helium, it will be a cheaper gas. And actually, when we went to the Air Liquide or Air Product or the people that provide this helium gas, actually to get this mixture, which is not commercially available on the market, is actually much more expensive than get a 10% helium mixture than to get a 97% minimum. So that was quite interesting. And in terms of thermal cycles, basically grouping the fugitive emission from ISO from 2 tests to 1 test. The ISO, I would say what we concluded was better, but the IOGP still gives you the trend. So if you have, I would say, an incorrect valve design, it will show it, but you will have less reproducibility that you would have for the ISO. And also at the lowest temperature, we observe the same phenomena, whereas it was at 150 on minus 29 with pure helium. So that's I think that's the end of my presentation. So thank you for your attention, and thank you to CETIM for their collaboration, and also to OMS Salaries that help us provide the valve. And as I mentioned, so this is a key topic for us. We are committed to reduce our methane emission by 80% by 8 years, from 2020 to 2030. So we need better, well, not better, but very good fugitive emission valve. And we have a lot of work to deliver that value. That's a strong commitment from our top management to our shareholders and all the financial community. So, thank you.
Thank you, LOＩC. Do you have some question for LOIC? Yeah.
Always me. Thank you, everybody. Thank you, LOIC. The question about the goals of reducing 80%.
Yes.
From 2020 to 2030. So now we're in 2022. How much has been reduced so far? Is it?
You know, we have been into the number. I don't really have the number of 2022. I would say, you know, the number I was based on is official publication from Total Energy that was published in 2019, so pre-COVID. So in 2000, after, you know, we had some variation of numbers because of our operation went up and down, but I would say that the reduction has not been very significant over this past, the first 2 years. So we still have a lot of work to do. So it's not only with valve, it's also, you know, with all the repairs and things like that. I think we have a presentation after from Scores, I believe. So there are a number of things we need to do. But valve is one of the key topics. That's why we are all pushing to have more fugitive emission. And I know also API committee starting to have API 6D committee starting also a new group to talk about fugitive emission. And this is something nobody wanted to hear a few years ago. Now everybody is coming on board. So to us, it's a very, very key challenge. So we know we talk about a lot about hydrogen, but for us, you know, the big problem is fugitive emission as well right now. So.
I think it's mostly with valves that are dynamic, because a static, let's say an on-off valve, isolation valves, they don't move much, so the stem is usually not leaking as much, and so mostly control valves is where your leaks are coming from?
Not really. Yes, you can have, maybe, you know, rising stem is obviously, you know, maybe more challenging, but from our perspective, we need to tackle, you know, each type of valve, because it could be it's not only the packing itself, it's also, you know, the way you assemble the valve. So it's about assembly the valve right, making sure, you know, it's maintained right. So it's all the full chain, I would say. So.
Right. So quarter turn control valves also of interest because they're easier to control emissions than rising stem?
Yes, they can be. I mean, there's a number of options, but each option has, you know, pro and cons. So, you know, in terms of controls, you know, ball valve is probably not the best, but yeah, it's something we are looking at. We are looking, you know, everybody is looking at many options now. So because, you know, we have, you know, as I mentioned, we have goals, and we need to achieve these goals, and it's now we have a lot of work to do, I would say. So we need everybody's help. So.
All right, we'll follow up. Thank you.
Okay, should be okay. Thank you, LOIC, for this presentation.